if you want to implement TinyBASIC using F# based on the template that comes with the course, you will need a few more constructs from the F# language that we didn't need in TinyML. So in this video, I will go through the various things from F# that you will need for writing the basic interpreter. There's a couple of things. First of all, in TinyML, we were running everything using the F# interactive REPL. So you just highlighted things and run it in the console. This time, we will actually want to use a project that you can run from a standalone terminal, because that way you can interact with it and you can give it some input. So we will need to. I will show you how to do that. We will also need to write code that runs and processes some user input. And to do that, we will need a sort of infinite loop, which we can encode in F# using recursion. And I will have to tell you what tail recursion is. In terms of the language itself, previously we mostly just used the discriminated union type. This time we will need records and tuples as well. So I'll cover more of the F# language basics. And especially for working with these lists of lines of source code, we will need some list processing functions. So I'll cover those as well. So F# is a .NET language, and we can use the .NET command to run and create projects. To create project, I can say .NET new. The type of the project, we just want a console project. And then I can specify that I want to create an F# project. If I do this, .NET will use the F# project template and give me a starting point with program fs, that's my source code, and demo fs_proj, which is the project file that describes things like references. I can run this by typing .NET run, and this compiles the project, generates a .NET executable, and runs it using the .NET runtime. So let's edit this. And here's the default generated template. After the project loads, so this takes a couple of seconds, you will also see this new tab appear here. And the tab is specifically generated for F#, where it sort of reads the project file, gives you all the information about the project. And as I said earlier, in F#, the order in which files are in your project actually matters. So here you can reorder the files in the project. And you can also sort of see the project just as a source code. So as an example, what I want to do is recreate that little demo I wrote earlier in BASIC, which puts stars all over your screen. And how do we do this in F#? Well, you can write things on screen just using console write. So F# has access to all the standard .NET APIs. And if we want to put the cursor somewhere on the screen, we can set the cursor left and the cursor top properties. I will want to use some random number. So I can create a .NET random number generator and set the left to the next random number. And the maximal value we can find here. There's a console window width that tells us the maximum. And the same thing I can do for top. Here we're going to use height. So this will now print a single star somewhere on the screen. Now, F# has both functional and some of the useful imperative constructs. So if I want to run this in a loop, I could actually just say, while true, do this. And if I run my program now, it will hopefully fill the screen with stars. So that worked. But this is not very useful. This way of writing code doesn't really work nicely if you need to keep some state. And that's what we will need in our basic interpreter. So instead, I want to use recursion. And I'm going to define a function called star that puts a star on the screen, and then calls itself again. And to do this, I have to mark it as recursive. And just to make this printing a little bit nicer, I can also say that the cursor should not be visible. So if I do this, then we will have the same program, but now written using recursion. If I run it, it does fill the screen with stars again. Okay, so there's one interesting thing going on here, because we have a recursive function, but this recursive function runs indefinitely, and we didn't get Stack Overflow exception, which is what you would get in many other languages. The trick here is that this recursive call to itself is the last thing that the function does. And if you have code like this, then F# can optimize it using a thing called tail-recursion, and it will not actually keep a record on the stack. In many cases, F# even sort of optimizes the code and compiles it into a loop. But in general, if you write functional recursive code where the last thing that it does is calls itself, then this will work even for long-running processes that would normally overflow the stack. To make this demo a little nicer, I want to do one more thing, and that's to sort of add some stars on the screen, but then also erase some that are already there. And so I'm going to write another function called white, and I will do the same thing there, except that I will put in a space. So this now would sort of, in every step, put one star, put one white space. The problem is there's very small chance that this would the white space would actually erase any of the stars that we have on the screen. So what I want to do instead is have some maybe run white 10 times and then run one star. I also forgot to call white here. So if I want it to actually work, I have to sort of call the white function from star and then call the star function from white. To put this differently, the idea here is that we have these two functions that represent the sort of two states, two logics that the program does, and they're mutually recursive, which you write using the let, rec, and construct. That means that they both can call each other. And so once we put some star on the screen, we switch to the other mode, put some white space on the screen. Once we do that, we switch back to the stars. And if I want to put multiple white characters on the screen, then what I can do here is say, I will call white with the number of white characters we want. And then I'm going to say, if this is 0, then switch to stars. Otherwise, continue putting white characters, but with one less iteration. If I run my code again, then this should now be sort of popping stars up on the screen, but also we have sort of 10 times more chance that we will erase a star. So some of the stars are disappearing again, and we have a nice starry screen. So this was showing how you create projects, how you print, and how the tail recursion works. And there's two more things that we will need in the core in TinyBASIC. First, we will work a lot with tuples, and we will write a lot of functions that work with tuples. So tuple in F# is just the type that represents a pair of values. The type is written with the star, so int star int means I've got a tuple that contains two different integers. We saw tuples in TinyML earlier, so you already know how tuples work. One interesting thing in F# is that when you're writing a function, there's a difference between a function that takes a tuple of arguments and a function that takes two separate arguments. So, for example, in the demo here, we are working with pairs of numbers that represent x and y coordinates. So here I'm going to create a tuple with 1 and 10, and here I'm deconstructing the tuple into the two pairs, the two individual values, x and y. If I want to write a function called rotate, I can use this notation, and what this means is that it's a function that takes a single value of type tuple as an argument. And immediately when I write this code, I'm deconstructing the tuple into the two components, x and y, and then I'm switching them. So this is a function that takes a tuple of two ints and produces a tuple of two ints. We can combine this with the usual way of writing functions with multiple arguments. So move x, for example, is a function that takes some value by how much, and a tuple of x and y, and it produces a new tuple, new x and y coordinates where the x is moved by a given number. And here the type of this function is that it's a function that takes an int, that's the by, takes a tuple, that's my x and y, and then produces a new tuple. And the nice thing about writing the code in this way is that you can then easily compose things. So if I take my point, pass it to rotate, I don't have to separate out the x and y, I just put the whole point there, but I can equally call rotate and put an inline tuple with 7 and 58. And then the result of rotate is again a tuple which I could pass to as the second argument of move x. So I can then also do things like take a tuple and use the tuple in a pattern matching construct. This example here shows somewhat arbitrary, just as an example, but it shows if we wanted to calculate an area, we could do this by just looking at one or the other value, and if those are 0, the result is going to be 0. And there's a few more sort of syntactic tricks that you can do, maybe to sort of make your code shorter that we will see later on. But the key thing is tuples are just an ordinary value, and if you use them in functions as arguments or as results, they still behave as tuples, and it's a separate thing than function that takes multiple arguments. I wanted to illustrate this a little bit more, and one interesting aspect of the kind of syntax of tuples is that there's a symmetry between the constructors that you use to create tuple values and the destructors that you use to decompose them. So if we look at all the different places where we construct tuples, there's the literal where we just put specific numbers. There's a tuple expression here where we have two variables that we use as the elements. There's an expression here where we compute one of the arguments. And interestingly enough, in here, when we use the pattern matching, I didn't put the parentheses around it because they're optional, but this is also creating a tuple, which we then immediately deconstruct and match against. We're doing this because in match, we want to be able to look at multiple different things at once. And the same syntax with the parentheses, one thing, another thing, is used to deconstruct tuples as well. So here, for example, we are taking a tuple and we're binding it to a pattern, and the pattern extracts the first and the second element of the tuple into variables, x and y, and the same thing is happening here. So when you write rotate parentheses x comma y, you're really writing a function that takes a thing, and the thing is matched against this pattern that decomposes tuples. So exactly the same thing is happening with all the other function definitions here that take a tuple as an argument. In the little function at the end, these two values, they're tuples as well, but we're not decomposing them. We're just keeping the tuple as a pair of values. And in the function area, all these patterns that have a comma in them, they're also decomposing the tuple into its individual components. So whenever you see a comma in F#, it's useful to think that this is a tuple, either a construction of a tuple or a deconstruction of a tuple. The last bit of F# that we will need is working with lists, because as I said before, we will need to keep a list of numbers that represent our source code. In F#, there's a type called list that represents a collection, a list, and F# is using the standard functional representation where a list is either an empty list or a const cell that consists of the head, the first element, and the rest of the list. And there's sort of shorthand syntax for just creating a list based on sort of fixed literal, but really underneath what this means is we want to create an empty list, then create a new list that starts with 4 followed by the empty list, then create a list that starts with 3 followed by the previous list, and so on. You can also create lists with shorthand to give a range. When you want to write some code that processes lists, the sort of low-level underlying approach is that we want to pattern match on a list. So when you use the match construct with a list, typically you will need two cases. One for the tail, meaning this is the one for the empty list, meaning what to do when the list is empty, and one for the head and tail case where we have some value followed by the rest of the list. When you're pattern matching, you can also match against a list of a fixed specific length. So here, this would just match if we had a list with 2 elements. And F# will check that you are covering all the cases. So if you, for example, included this case but missed one of these 2, the compiler will tell you you're missing a case. Just like tuples, where we had the pattern with the comma to deconstruct a value, these things with the double colon or the empty list or the fixed list, these are patterns. And so they can appear inside match, but equally they can appear in variable binding or in arguments of a function. In practice, this is not very useful because they are only partial. They're not covering all the possible values of a list. So if you write code like this, it will crash sooner or later. But the syntax allows this because there's this sort of nice symmetry where you can use patterns anywhere. If you're doing something for real with F#, with lists, you will probably want to use higher order functions like list.map. I want to show you an example of working with lists in F#, and I have a sample script file here where I create already a list of strings, and the list of strings here contains the populations of different EU countries. So if I load this, I'll be using F# interactive again. Then this loads the list, and now we have a list of numbers. If you want to do a list of strings, if you want to do anything useful with this, we will need to find some way of parsing this. So I'll take one country as an example, and let's try to parse this. So what I can do to parse the string is I will call split, which is just the normal .NET function to split a string. And this gives me an array. And this will typically be an array of 2 elements, if my input is correct. And just like I have this pattern matching on lists, F# has a syntax for pattern matching on arrays. So I can write the code like this and pattern match on the country name and the country population. These 2 things are currently strings, so let's call them sname and spop. And well, maybe I will start just by returning those strings. And here I need to have a semicolon because that's the separator for lists. I don't have a tuple here, but I do need a comma here because I want to return a tuple. If the split doesn't give me a 2-element array, something is wrong. So I will just say invalid input. And I can sort of run this to see if it works. And indeed, I get back a pair of strings. But I also want to parse the population. And in F#, I can call the try parse operation from .NET on my string. And in .NET, this actually uses output parameters, but F# maps this to a function that returns a tuple, where the first is a Boolean indicating whether it worked, and the second now would be the population. So if we return the string name of the country and the population, and if this fails, we will just say parsing failed. So now I'm able to parse a country, and I tested this on one country, but I can turn this into a function that takes a country. And for this particular case, I will need a type annotation because otherwise F# doesn't know what country is. And if I want to call method on it, it needs to know what type of object this is. So I will have to annotate this with a string. And now I have a parse country function. So now we're able to do something like call list.map, use the parse country function, and run it on all the elements of my EU raw list and turn this into EU. And now we can see we have a list containing strings and ints as a tuple. Now, one thing we might want to do is to calculate the average population of a country. In reality, you could do this using the average function that the list module has. But let's make it a little bit more interesting. Let's explore a few other functions that are here. So I can use list.length to get the number of countries in my list. And I can also use the list sum function to sum a list that contains numbers. Now, my list currently doesn't contain numbers, it contains pairs. So I will first need to do one more map. And here I need to decompose the tuple of the individual element into the name and the population and extract the population. So this works. And F# does have a built-in function to take the second element of a 2-element tuple. So I can actually just write list map snd. And this is now a list that I can sum. So I can pass this to the sum function. And this is my total population. So we've got the total population. And then if I divide the total population by the number of countries, I get the average. And maybe what we can do more is to find the number of countries that are bigger than the average and the number of countries that are smaller than the average. So for this, there's another useful function called filter. And this takes a function where we specify some predicate. So if we want countries that are smaller than the average, then we can say we want countries smaller than the average. and we get a list of countries back. Here in this pattern, I'm not using the name. So in F# you can replace that with underscore, and that's a special pattern that just ignores whatever is get there. And this means you avoid warnings about unused variables. And now I can also take the length of this list. And I made a mistake. I didn't run the previous line, so I didn't have average defined. But if I fix this, then I know there's 20 countries that are smaller than the average and 7 countries that are bigger than the average. So this was kind of a basic way of writing the code. F# has one very handy feature called the pipe operator. And in the previous snippet, I had a lot of nesting and a lot of parentheses. And to avoid this, F# defines this pipe operator, which is available in the standard library, but you can actually define it yourself with something like 10 lines of code. And this is also something that's roughly corresponding to the pipe in Bash. And it's a feature of F# that has been copied by a lot of other languages, including R. So the idea of the pipe operator is that we can then take the input and put it on the left of the pipe operator. And the pipe operator takes the argument on the left, takes a function on the right, and passes the argument to the function. And this crucially relies on the fact that F# uses this curried representation of functions, where listmap is a function that takes one argument and then returns a function that takes the further arguments. So because the selected thing now is itself a function, I can just use it as an argument to the pipe operator, and I can rewrite all the code I had so far using the pipe operator. And this really makes the code nicer once you have longer chains of operations where you previously needed a lot of nesting. Because now, for example, here I can just say, take the EU list, pass it to map, take the result of what that did and pass it to sum. And again, I can do the same thing here, where my code will be a lot nicer if I say, take the list, pass it to filter, and then pass it to the length operation. So this means exactly the same thing, but it's just a much nicer way of writing the code. And there's one more thing that we will need in the basic implementation, and that's working with options and functions that return an optional value as an argument. So one example of this is the try-find function. And what try-find does, and we can sort of see it from the type, is that it takes a list of inputs, takes some predicate, and if there is an element for which this returns true, then it returns the element. But if no, it returns a value that represents there was no such element. So the option is a two-case union that can be either sum containing a value or none, indicating that there's no result. So for example, if I want to, for example, find a country that starts with a particular prefix, I can take my countries and say, can we find a country? And here I don't need the population, just the name, where the name starts with this given input. So for GR, if we do this, the result will be Greece. If we were looking for anything starting with great, then the result is none. And I will store this into a variable, and then we can sort of say, if we want to write any code that works with this result, I have to pattern match on the result and say, if this is some result, so if this is some country, then we can print, and the country is, again, this tuple of string and population. So I will take name and population. Then we can print the name of the country followed by the population. But if this is none, then we will print no such country. I could wrap this inside a function find by prefix input, and I do have to specify that the input is of type string. And now I have a function that searches my list for a country. So we can try CZ. That gives us country. But if we say UK, then there's no such country. So this is covering more features of the F# language, focused on the ones that you will need to implement your TinyBASIC interpreter.